So yes, I'm from the French University for Civil Aviation, ENAC, and University of Toulouse. So thank you for listening to me and good afternoon. So I will be presenting this talk on behalf of my colleagues at ENAC, at Deep Blue in Italy, and Matt in Malta. So I will be talking about the system, which we call Vizir. And as you said just a few seconds ago, it's a visual language in order to operate, to author and operate automation on an airport. So first, a few words on the context. It's about air traffic control in the tower. So you can see here a nice image of the settings of a tower. So you see a lot of people and systems, and obviously planes on the ground. So the aim of airport traffic control is to organize the movements of aircraft in the air, the landing and departing aircraft, or on the ground, on the runway, on the taxiways, and on parking areas. So, the goal is also to organize the movements of other vehicles, like passenger buses, trucks, and cars. It's a complex hybrid system. There are many humans and many automated processes that interact with each other. And the system has two main objectives. It's safety and capacity. So safety is the ability for the system to prevent accident and incident, and capacity, which is to maximize the number of flights. So the controllers are in charge of the system. Controllers are professionally trained and are highly skilled professional, highly skilled at maximizing both security and capacity. And actually the system works very well. Capacity is still expanding and safety is better every year. I don't know if you heard that in last year has seen no accident in aviation. I'm commercial aviation, of course. Still, aviation institutions think that we will hit a wall someday, so they still want to improve safety and capacity. And automation is one of the key solutions proposed by international air transport programs, such as CESAR in Europe or NextGen in the US. So automation is the execution by a machine agent of a function previously carried out by a human. So, of course, there are assets that are expected from automation. So the offload of monotonous tasks from the human to the machines, a greater efficiency, and a greater capacity. So you might have noticed that automation might improve safety and capacity in the title. The might is important. It's because automation is also problematic. As previous studies have shown that users have a low sense of trust and substantial degree of confusion regarding the operations of opaque systems. So this has the consequence that the automation is difficult to predict. And of course, one of the problems here, as it's written in the sentence, is this notion of opacity. So this is the main idea behind our work. If the automation lacks visibility, then show it. Okay, so that's why we design Vizir. So it's a graphical language in order to show the automation. But it's not the only idea. The second idea is that we have this assumption. It's that automation designed with and by controllers, it's ADCOs, this is the acronym, will maximize relevance, minimize surprising behavior, and maximize predictability. So we want ADCOs to participate to the design of their own automation. So that's the domain-specific part of Vizir. So how did we do that? So we used a participatory design process. So we went to the actual settings. So this is a picture of the actual settings in Malta Airport. And we work together with the ADCOs, the controllers, in order to design how a system could support the design of automation, the authoring of automation. Of course, we relied also on previous work, especially on visual languages, such as for scientists, for example, or even for non-professional programmers, or for video game programmers, or even video games. Video games, you can program some automation, like, for example, in a real-time strategy game, from music as well, and even from music automation that you perform during the performance of the musical piece. And of course, we relied on previous ATC research projects. And actually, ATC is a great provider of many interesting use cases in the HCI area. So after this analysis, we divide the set of requirements consider the existing scenarios, of course. We want to support the current activity. Define language constructs relevant to air traffic control. Language constructs usable by air traffic controllers. We wanted to foster predictability of the automation and handover by the human. And we wanted to foster efficient and scalable authoring. So let's dig into authoring first. If you start the application, Vizir, you will see this first screen, and you can see that there is the map of the airport. And actually, the controllers rely extensively on both the airport map and the radar image, which often includes an airport map, to accomplish the task because it offers a clear landmark that supports reasoning. So to support the tasks, automation must be visible and correlated to the airport map. So let's see a few basic interactions in order to author some automation. So here you have a toolbar on which you can choose and drag and drop some tools. So for example, here this component which is an enter-leave zone. You can drag an alarm and connect the enter-leave zone to the alarm and then test the behavior of the automation using a fake plane, fake flight. So you see that when you drag the flight over the enter-leave zone, the alarm is ringing. Okay, so this is the very basic interaction. And now let's dig into another one, a more complex one. So here the user will build a data flow. So starting from the previous example, we add another zone, an AND operator, and we connect both enter-leave zone to the AND operator input and the output to the alarm. So actually this one, then the user will specify that the runway is occupied using what we call an occupied puck. And this is something that we borrowed from the observation in the tower. And then you can see that it works. And actually it's a meaningful automation here because it will trigger a go-around to the pilot if the landing aircraft is landing on a non-free runway. So the idea of borrowing the occupied puck, it's because we don't know exactly when the runway will be occupied. So it happens sometimes that it could be a car, for example, or a rare event like, for example, a fire, because the grass is dry enough in the summer so that when a large flight departs, it will burn the grass. So sometimes it happens. So you need to have a way to specify that the runway is occupied, whatever the reason. So we've seen two examples with alarms. Now let's see another example, which is related to what we call stop bars. So stop bars are lights that are unidirectional lights that provide protection at runway and taxiway intersections and reduce the risk of runway incursions. So pilot and vehicle operators are required to stop at the runway hold point and wait for the controller to switch off the stop bar. So let's see how we can specify that with Vizir. So you still have an enter-leave zone here, and you see here the aircraft which stops here at the stop bar, and then the stop bar is switched off because this flight has left the enter-leave zone here. So you can see the difference between the other example. Here, the zone is cut off. It's not as long as the runway because it specifies that as soon as a flight has exited here, that is just a little bit after the intersection, then the other flight can enter the runway. So there could be two flights on the runway, and it's not a problem. And it's really an example of how controllers balance safety and capacity. And finally, another example in which we can see that the user can switch on and off the display of state machines that control the actual behavior and the actual state of of the runway. So Vizir enables users to do some data flows and connect them to state machines seamlessly. Okay, another example with the leverage of the interleave zone. So here we have an interleave zone that actually counts the number of flights. And you can see here, there is a gauge and a little dot here. And the interleave zone is actually triggered by the fact that the little dot will enter the interleave zones. And it will trigger, in turn, a change here in this strategy box. So this strategy is another, it controls the way another algorithm computes the sequence of departure. So this automation here specifies that whenever the parking area is full, then you have to change the strategy. And you have to pass from a less fuel consumption strategy to a runway user strategy. As I said before, one of the problems with automation is that people want to be in the control, and especially the controllers. So let's see how we can transfer the control from the controller or to the controller. So let's start from the previous example. On the previous example, the strategy is changed automatically, but here the user specified that he will be or she will be in charge of this change. So whenever the change is triggered, there is a confirmation box that the user can actually click on it in order to confirm that the strategies can be changed. Back to the stop bar. As I said, the stop bar should be switched off in order for a flight to enter the runway. But there should be also an order, a clearance by the controller. And the controller actually speaks to the radio. The controller will communicate with the pilots through the use of a radio. And of course it takes time, but we envisioned that we could also transfer this kind of activity from the controller to the machine by the use of a speech interface or a synthesized voice over the radio.
AF123 cleared to backtrack.
So this one, it's another way to offload the role of the controller to a machine, and that would mimics how the system can be used with the machinery instead of a human. This one is tricky, actually. When we show that to the controller, one of them said, okay, the runway is more important than my house. So I will never let an automation do that. And he was a bit afraid that the automation could talk in an unattended way. So, but then these are some ideas that we can explore anyway. Finally, the operation. As I said before, the automation should be predictable. So we provide the users with tools to help them visualize the behavior of the automation in the future. So we design a time slider, but we also design an interaction that enables a user to drag a flight along its planned path. So it's, when you click on it, you see the planned path, and you can drag the flight and see that the other flight will enter the runway because the automation will be triggered. So you can see in the future what the automation will do and predict and better predict what will happen. And the difference between a time slider and this kind of slider is that we use the location instead of time. And it's very important because you want to know which automation will be triggered when, where actually the flight should be at some intersection. So you want to assess that. And finally, you can control the program visibility during operation. So in alarms, whenever the alarms is triggered, then the program appears, the automation appears, so that the user is able to understand why this happened, or he can or she can trigger the progressive disclosure on the automation in order to reveal the automation. Okay, so here are the design principles that we follow. That we followed during the design of those interactions. So we have a continuum of usage and progressive disclosure. So we envision that the user will authoring ahead of time the map and programming rules and constraints from what we call the operational manual so much ahead of time. And when programming local automation according to the places of the airport, or just in time while controlling by anticipating and quickly programming clearances in advance, or simply reacting to behavior triggered by automation, or even simply supervising. We have space-based and event-based construct instead of the use of timers, and we leverage the use of interleave zone to the substrate, and we try to maximize the use of interleave zones. We try to make the current state and future behavior visible, as you could see here with the alarm, the fact that the operator here will be highlighted whenever the input gets triggered, or by using the direct manipulation along the path. And we provide seamless and simple hybrid control. So what do I mean by seamless and simple hybrid control? Seamless is that programming constructs are designed to be indifferently performed by humans and automation. And so we can connect things seamlessly between humans and the automation, the machinery. But we have also simple hybrid control because we can provide some way to put the user back into control. So with this hand here, or by letting the user click on the input in order to trigger the input. And also we try to foster interaction-oriented programming using, but I can talk about that later, using a framework that is specialized in the programming of interaction-oriented system. We did a few evaluations, but very, very informal. And what we had here is that people were able to design some automation by themselves. They were able to design 3 automation in less than 10 minutes, which is, of course, not a full assessment, but it's something that is going in the right direction. So I'm finishing now as a conclusion. I have presented Vizir, DSGL, Domain-Specific Graphical Language and Environment, that combines visual interaction-oriented programming constructs with activity-related geographical areas and events, that offers back and forth transfer of control between humans and machinery, explicit human-controlled constructs, graphical substrates, and means to scale up with multiple automations, and that implements the design principles that may be useful for other similar systems. Of course, there are a lot of threats to validity, and I'm sure you have noticed that. It might be too peculiar. There is no assessment of the automation visibility hypothesis and no test of the user's cognitive load. And it's only a prototype. So thank you very much. If you have any questions, I would be glad to answer them. Thank you.
So we have time for a couple of questions, so please state your affiliation before you state the question.
Hi, thank you for the great talk, really interesting. I'm David from ETH Zurich. So I wanted to ask you whether you thought about visual clutter. So you were already putting these different elements in it, and so this was like obviously like a prototypical kind of airport, yes. Right? So if we were at Frankfurt or something, this could get really full, right? And did you evaluate that? Did you discuss with the ATCOs whether they have any thoughts on that?
Well, actually, the airport is a real one. Even if it's a small one, it's okay, a real one. No problem. It's the Malta's airport, actually. Okay. And yes, of course, when you talk about visual languages, this is always the problem that comes first. Mm-hmm. But I think it's exactly the same that with textual program. You can see a program, a single program at once, yeah, on one screen. So what you do progressive disclosure. So that's what we design here. So maybe a little bit of the video while I talk. You have like, it's really like an editor, so you can have like files. Sorry, there is no. Could you put back the video, please? Too bad. Is it possible to have the? Thank you. Okay, so maybe I can go back a little bit. So you have here on the side a file browser. So you can choose to display an automation or not. It's really like another text file, for example. And you have a set of tabs also. It's really not different than any file editor. So it's a way to mitigate this complexity.
Okay, thank you.
So we'll take one last question while the second speaker is setting up.
Hi there, I'm Connor from Uber. Thank you so much for the great presentation. I'm wondering if you've considered tools to allow ATCOs to compare multiple programs that they might have designed for the same airport, or to abstract over a spectrum of possible programs to find an optimal one, maybe one that helps them manage resources as efficiently as possible or manages capacity the best.
Sorry, I had a hard time to hear, but you asked me if people were able to compare programs, that's it, or?
Yeah, I'm wondering if there's any functionality that you've explored in the same visual language to help ATCOs discover an optimum among a set of possibilities that they could design.
No, actually, this is really a design work, so we didn't go very deep in with ADCOs to design real stuff. So this part is really the next part of the project.
Thank you.
Okay, let's thank the speaker.